In the design and analysis of algorithms, both this course and its predecessor, we've covered a lot of famous algorithms. We've covered a lot of fundamental data structures. We've covered lots of killer applications. And despite the fact that I've tried to use our time together in the optimal way, giving you the most bang for the buck, there are fundamental topics we have not had a chance to cover. In these final few videos, I want to talk a little bit about things we didn't talk about. I have a few goals. The first goal is to give you a little bit of literacy in a few more techniques, so at least you've heard of things like bipartite matching and the maximum flow problem, and you're aware that there are good algorithms for those sorts of problems. Secondly, I want to get you excited to do a little bit more study, either through further courses or on your own. And indeed, generally the topics that I'll mention in these final few videos are covered in your more comprehensive textbooks on algorithms. Finally, I hope to convey something I've mentioned in passing in the past, which is that algorithms is not an ossified field. Rather, it's a vibrant area of research. There are still lots of things about fundamental problems and models that we don't yet understand. Let's get the ball rolling with a very fun classical problem known as stable matching. We're going to think of stable matching as a graph problem, and there's going to be two sets of nodes, two sets of vertices, capital U and capital V. For historical reasons, we will call these sets the men and the women, respectively. A non-essential assumption that we'll make for simplicity is that these two sets of nodes have equal cardinality. Call that common size n. So for example, maybe n equals 3, and we can call the first set of nodes A, B, and C, and the second set of nodes D, E, and F. Now what's really important about the stable matching problem is that every node has preferences. There are things that it wants more than others. Specifically, each node in U has a ranked list of the nodes in V. Each node in V has a ranked list of the nodes in U. So in this example, maybe A, B, and C are all on the same page. They all agree that D is really the best node. It's better than E, but E is definitely better than F. That is, maybe every single node on the left-hand side has the ranked list D followed by E followed by F. By contrast, maybe there's heterogeneous preferences amongst vertices in capital V. Maybe D thinks A is better than B is better than C, while E prefers B to C to A, and finally F prefers C to A to B. So what might these nodes and these ranked lists represent? Well, imagine, for example, that one set is colleges and the other set is applicants, recent high school graduates. Each college has a ranking of the applicants based on things like test scores, grades, and the fit that student is for the college. And each student similarly has a ranking over the colleges of which ones it prefers to go to over others. As another example, you might think about medical residents, that is, people who just finished medical school looking for a residency, and the other side being hospitals. Again, hospitals are going to have a preference over which recent graduates they accept as residents. Potential residents, of course, have preferences over which hospital they get assigned to. So given this data, two sets of nodes, and these ranked lists, we're interested in computing a stable matching. So what's a stable matching? Well, first of all, it better be a perfect matching. And a perfect matching means that each node on the left, each node of U, is matched to exactly one node of V and vice versa. In addition to being a perfect matching, it should also be stable in the sense that there should be no blocking pair. What that means is that if you look at any pair of nodes, little u from capital U, little v from capital V, if little u and little v are not matched, there better be a good reason for them not being matched. Specifically, little u better strictly prefer who it is matched to, call that v prime, to this alternative v, or if that's not the case, it better be that little v strictly prefers the node it's matched to, call it u prime, compared to the alternative little u. So what's the motivation for this definition? Well, think about any perfect matching that fails this stability property. You're really asking for trouble for that kind of matching. Specifically, U, with its wandering eye, will spy V, and it prefers V over the node V prime to which it was assigned. Similarly, V is going to return that gaze. V prefers U by assumption that the stability property fails over the node U prime to which it was matched. So U and V are going to have an incentive to essentially elope and disrupt this whole assignment. Imagine, for example, that U is a student and V is a college, and you have a matching that fails the stability property. Then this pair, this student and this college, has an incentive to do a sort of backroom deal after the fact. You might want to withdraw its commitment from its assigned college V prime to try to get into V instead, and V to college actually wants to sort of withdraw its offer from its student U prime to give it to U instead. So that's an unstable matching, but as long as there's no blocking pair of this form, and for every pair which is not matched together, there's a good reason for it, then we deem it a stable matching. Let me tell you about an extremely elegant and justly famous algorithm for computing a stable matching, the Gale-Shapley proposal algorithm. Lloyd Shapley was one of the recipients of the 2012 Nobel Prize in Economics, in large part for this algorithm. Had David Gale still been alive, he surely would have been a co-recipient of that Nobel Prize as well. Let me explain the algorithm in an example, then I'll give you the general pseudocode. We start with the empty matching, with nobody matched with anybody else. And as long as there's some man, some node on the left-hand side, which isn't matched to some woman, we pick an arbitrary unattached man, and we let it propose to a woman of its choice. So we might start, for example, with the man C. C says, well, my favorite woman is D, so let me start by proposing to the woman D. Now, D isn't necessarily very impressed with C. Notice C is last in D's preference list. But with a lack of other proposals at the moment, the node D tentatively accepts this proposal from C. Now we proceed to the next iteration of the while loop. We look for a man that is unattached. So maybe we pick B. B now gets its shot at proposing to its favorite woman. In this case, it is also D. So now the node D has a bit of leverage. It has two competing offers from the nodes B and C, and of course it retains the offer from the preferred suitor. In this case, D prefers B to C, so the edge between C and D gets deleted and replaced with the edge between B and D. So now both of the men A and C are unattached. Perhaps in the next iteration we let the node A gets its shot. It again proposes to the node D, and again D prefers A to B, so the edge between A and D is going to replace the edge between B and D. So we now again have two unattached men, B and C. Let's say we pick C next. So C gets to propose to whatever woman it wants, and D is its favorite, but it's already been rejected by D. And in the algorithm, a man will never re-propose to a woman who has previously rejected him. So next on C's list is the woman E, and so E has not had any other offers, so E tentatively accepts the proposal from C. But now, once B gets a chance, B will also propose next to E. That's B's next favorite, and it's already been rejected by D. And E prefers B to C, so we will replace the edge between C and E with the edge between B and E. And so now finally, the man C is the only one that remains unattached, and it has no choice but to propose to its final option, the node F. F actually happily accepts that because C is on the top of F's list. And that leaves us with the matching that matches A with D, B with E, and C with F. This is clearly a perfect matching. I'll let you check that it's also a stable matching. Having traced through this example, I hope the pseudocode for the general algorithm will not surprise you. So we have a main while loop, and in each iteration we pick some man who is not yet engaged to any woman. Call that man U. U then proposes to his favorite woman, the top-ranked woman, with the constraint that he will not propose a second time to any woman who's already rejected him. Each woman then behaves in the obvious way, which is to keep track of all of the suitors, all of the men that have proposed to her, and to retain as a tentative engagement only the proposal from their favorite, that is, highest ranked suitor. Notice this algorithm maintains the invariant that the current set of engagements is a matching. Not necessarily a perfect matching, but a matching. That is, at any given time, a man is engaged tentatively to at most one woman, and every woman is tentatively engaged to at most one man. The Gale-Shapley theorem states that not only does this algorithm terminate quickly, not only does it terminate quickly with a perfect matching, but in fact it terminates quickly, namely in a quadratic number of iterations at most, with a stable matching. In particular, this theorem, this algorithm, provides a constructive proof that a stable matching always exists, no matter what the preference lists of the nodes are. A highly non-obvious fact. The proof of the Gale-Shapley theorem is as elegant as the algorithm. Let me show it to you now. So first of all, why does the algorithm converge in a quadratic number of iterations? Well, no man proposes to a woman twice. Therefore, each man makes at most n proposals. There are only n men, so that's at most n squared proposals overall. Secondly, when the Gale-Shapley algorithm terminates, it does so with a perfect matching. Indeed, it's a stable matching, but let's just, for the moment, prove that it's a perfect matching. To see this, let's suppose the contrary. Let's suppose that when it halts, it does not halt with a perfect matching. That means, in particular, some man is assigned to no woman. How could that have happened? Well, it must have been that the man fell off the end of his ranked list. He proposed to every single one of the n women and was rejected by all of them. So how could this have happened? Well, notice that for a man to be rejected by a woman, it must be that the woman has some other offer from some other man that she likes better. That is, rejections happen only by a woman who is engaged to somebody else. So by virtue of this man being rejected by all n women got engaged at some point in the algorithm. Moreover, if you inspect the algorithm, you'll notice that once a woman is engaged to somebody, she will remain engaged forevermore. The only thing that changes is the woman is engaged to men that she likes better and better as the algorithm proceeds. So a man rejected by everybody implies that all women get engaged at some point in the algorithm, which means that they're all engaged at the end of the algorithm. But there's an equal number of men and women. So there's no way all women are engaged at the end and some man is not engaged. If all women are engaged, all men must be engaged as well. Finally, why is the perfect matching computed by the Gale-Shapley proposal algorithm not just perfect, but more generally stable? To see why this is true, let's prove that there's no blocking pair. That is, let's consider an arbitrary unmatched man U and woman V. Now, either the man U proposed to the woman V at some point in the proposal algorithm, or he didn't. Let's treat those two cases separately. So let's first suppose that at no point in the algorithm did the man U propose to the woman V. So what's the behavior of a man in the proposal algorithm? Well, a man simply proposes to the women on his list one at a time in turn as necessary. And the woman to whom a man winds up matched at the end of the algorithm is the last woman to whom he proposed. So if the man U never got around to proposing to the woman V, that just means he never searched that far down in his preference list. And he wound up, at the conclusion of the algorithm, matched with the woman he prefers to the woman V. And so that's sufficient to claim that UV is not a blocking pair. Suppose, on the other hand, U did propose to the woman V at some point in the algorithm. Why did they not wind up matched? Well, it must be because the woman V got a preferred offer, an offer from some man she prefers to the man U. Now, something we mentioned earlier is that over the course of the algorithm, a woman just winds up being engaged to men that she prefers more and more. So if at any point she winds up engaged to a man she prefers to you, then at the end of the algorithm, she will be engaged, matched with a man that she prefers to you. And again, that implies that UV is not a blocking pair. Since UV was arbitrary, this is a stable matching. That completes the proof of the Gale-Shapley theorem.